We are going to start with the heat equation first. After that, wave equation, and lastly, the Laplace equation. So given the general form of heat equation, del square U del T equals alpha square del square U del X square. So in terms of heat equation, U represent the temperature, T of course time, and X is the spatial coordinate. Okay, so ut equals alpha square uxx. Okay, given x in the range of 0 to L, t of course positive because of the time, and this equation has the initial condition. It means that at time t equal to 0, so the temperature value depends on some function fx. So in the exam, you will be given the function fx here. And we should also have the boundary conditions. Okay, so in the syllabus, we'll have only two types of boundary conditions. Okay, we are going to have example on the zero endpoints. Okay, boundary condition. Zero endpoints means the temperature value at both endpoints are zero, and the second type is the insulated endpoints. Okay, insulated endpoints meaning that at the end of the endpoints, there will be no heat flow coming out, okay, going out or coming in. Okay, and in the literature, in the textbook, you might see the mixed endpoints as well. Okay, but in the syllabus, we only discuss zero endpoints and insulated endpoints. Okay, so the heat equation here, back to the heat equation. So in terms of uh, diagram, we can imagine we have a rod. Okay, a rod. So the first case we have zero endpoints. So at the left and right endpoints, we have the temperature value is 0. Okay, so basically we want to know. So this is the spatial coordinates, meaning that the x coordinate. Okay, so if we have a heat somewhere here, if we put heat somewhere here, okay, so at time the initial time, so suppose, yeah, somewhere here is the highest temperature value. Okay, so basically we can illustrate in terms of graph. So if this is x and this is u, okay, so somewhere here, okay, maybe we have here x3, for example. Okay, so the temperature somewhere here should be high. Okay, so somewhere here. Okay, and maybe somewhere here x2 and this is x4, the temperature value, it might be here and here, might be somewhere here. And x1, okay, should be lower because the heat, okay, because the heat is at the middle. So if we have x5 somewhere here, okay, so we might have a value like that. Okay, so this is when t equal to 0. So we should know that t is the time, so time evolve. Okay, so when t equal to 5, for example, so we can expect that what happened to the x3. Okay, so the heat is going to be flowing to the left and right direction. Okay, so when t equals 5, for example, we can expect at x3 the temperature value somehow it might be dropped. Okay, and x2, okay, might be higher, and x4, okay, could be higher. Okay, because of the um, flow of the heat. Okay, so if we connect all the nodes, then we have that kind of graph. Okay, so that's the idea of knowing the solution to the heat equation so that we can see the changes, okay, in terms of the temperature, okay, with respect to the time and also with respect to the spatial coordinate. Okay, so basically, if someone asks you what is the temperature value at x equals 5 at time t equal 2 seconds, then okay, you should be able, okay, to know what is the temperature value at that time at that location. All right. So let's see how do we solve the heat equation using separation of variables method. Okay. So take the example 1 here. Okay, we have the 0 endpoints. Use the method of separation of variables to solve the heat equation given here. So you can see the alpha square here is 4. And the x interval is from 0 to 1. So we can imagine we have a rod with a length of 1. Okay. And the initial condition that's given to us is x over 4. All right. Okay, so in general, we have, I think, around 5 types, okay, 5 steps to get the solution to the PDE. Okay, so the first step is what we have done earlier, okay, which is to reduce the PDE to the 2 ODEs. Okay, let's try to do one more time. Okay, so first of all, the assumption, okay, the assumption of the final solution. Okay, so we are going to let the solution to be in the form of x times t. X is the function of small x and t is the function of time. Okay, so I'm going to denote this one as asterisk equation. Okay, later we'll refer to this equation few times. Okay, and the heat equation that is given to us just now is ut equals 4 uxx, right? Let us confirm this one. Okay, right. Okay, so first of all, we need to get the ut. Okay, so we differentiate the right hand side of the equation with respect to t, so we have xt prime, and in the heat equation we also have uxx, then we have x double prime t. Okay, so then therefore we substitute, okay, substitute in the PDE, meaning that the given heat equation, so I'm going to put this one as equation 1 maybe, okay, in the PDE 1. Okay, then we are going to have x t prime, okay, equals 4 ux, sorry, 4 x double prime t. Okay, and then separate the variables. So we put x double prime to be on the top. Okay, so supposed to be over x. Okay, equals then t prime over 4t. Okay, and we know that the left hand side should be equivalent to the right hand side only when they are both constant. Okay, so we denote as lambda. So therefore, okay, if we take x double prime over x equals lambda, then we are going to have x double prime minus lambda x equal to 0. So somehow I'm going to use this one equation 1. So let's put this one as A. Okay, so A here. And if we consider the t prime over 4t equals lambda, then we are going to have t prime minus 4 lambda t equal to 0. Okay, so we are now have the 2 ODEs. Okay, we have reduced the PDE to the 2 ODEs. That is our first step. All right. So, second step is to form the boundary conditions. So, BC stand for boundary conditions for the ODE by applying the given boundary conditions. Okay, so in the problem, we have the boundary condition. So, this one, but these conditions, these boundary conditions are for the PDE given here. Okay, so we have formed our ODE here. So in order to solve the ODE here, we need to form our own boundary conditions for these ODEs. Okay, because we know that by solving the ODE, somehow in the process, we come out with the constants. Okay, so we need the boundary conditions in order to know the constant value. Okay, so step number 2 is to form the boundary conditions for the ODE. Okay, how we are going to do that? Basically by applying the given boundary condition. Given here meaning implies the given boundary conditions given in the problem. All right. So the first boundary condition that is given to us is here. Okay, u0t equal to 0. Okay, so we are going to refer to u0t equal to 0. All right. So now, based on the equation asterisk here, okay, when x equal to 0, so this one meaning that x equal to 0, u equal to 0. Okay, so from this equation, okay, then we know that x of 0, p of t equal to 0. Okay, because the conditions given says that when x is 0, okay, t is t, then the value of u is 0. Okay, so at the right hand side here we have 0. Okay, this one equal to 0, so this one is basically u. Okay, referring to this is u, which is 0. And at the right hand side when x equal to 0, so we have x 0 t of t. All right. So by looking at this equation here, we know that t of t cannot be 0. Okay. Why do you think t of t cannot be 0? All right. So if t is 0, okay, if t is 0, then we are going to see that, okay, this equation will be 0. Whole thing here is going to be 0. Okay. If t is 0, so we have 0 times x, so everything will be 0. So it means u equal to 0, which is not logic. Okay, it doesn't make sense to our application. So u equal to 0, meaning that for whatever value of x, whatever value of t, the temperature value is always 0. That what it means. Okay, which is not logic. Okay, it doesn't make sense. Okay, so t of t cannot be 0 because by doing that, the temperature value u is going to be 0, which is not what we want. Okay, so since t of t cannot be 0, so the only thing that is going to be 0 is x of 0, of course. Okay, so only then the equation that we have here is valid. Okay, x of 0 equal to 0. So this is okay. Okay, x of 0 equal to 0 is okay because the x value is 0 only when the small x is 0. Okay, at any other points, they are not 0. So at any other points, we can ensure that the u is not 0. Okay. And that is for the first condition. The second condition that is given to us is u1t equal to 0, basically at the right point. Okay, so again from the same equation, from this equation, okay, this equation here, so when x is 1, so we have x1 t of t equal to 0. So the same justification, t of t cannot be 0, then x of 1 need to be 0. So these two are basically the boundary conditions for the ODEs. Okay, so we are going to use these boundary conditions later in solving the equation. Okay, so I put the three important equations here so that I don't have to scroll up and down. All right, step number 3 is to consider all cases of lambda. Okay, so now look back at equation 1 and 2 here. Okay, so we have the lambda involved. All right, so lambda is a constant. So whenever we say the constant, okay, it can be three possibilities. Constants means it can be positive. Okay, lambda can be positive. Lambda also can be negative. Okay, they are still constant. Or lambda can be 0. Okay, so there are three cases of lambda. So we are going to consider each one of them. Okay, see what happened when lambda is 0, what happened if lambda is positive, and what happened if lambda is negative. Okay, so if we look at the star equation here, so this is our aim. Okay, so we want to know what is the equation x. So equation x comes from solving equation 1. T comes from solving equation 2. Okay, so we are going to solve two equations, 1 and 2, so that we can put in the equation star here. That's going to be our answer later. All right, so first case is to consider when lambda equal to 0. All right, so when lambda equal to 0, from equation 1, when lambda is 0, then we are going to have x double prime equal to 0. Okay, so just like what we have in the second equation. Okay, second chapter, is this that in the second chapter we are dealing with the y, okay, y double prime and so on. All right, so this is basically the same thing. So this is homogeneous equation. Okay, homogeneous equation. Okay, but we don't have the term first derivative and we don't have the x. Okay, but it's okay. It's still homogeneous equation. So how do we solve the homogeneous equation? So first of all, we take the characteristic equation. So x double prime correspond to the m square. So we have m square equal to 0, meaning that we have two roots m1 and m2 which are both 0. So when we have both 0 roots, meaning that we have the equal roots. Okay, in that case, then the solution should be in the form of, sorry, it should be capital. Okay, so x of x equals to a exponent m1 x plus, okay, sorry, it should be in the form of a plus bx, okay, multiply with the exponent m1 or m2, which is 0. So basically, we don't really write that part. Okay, so x is a plus bx. Right, so that's the equation for the x. All right, so now we need to get the constant a and b. Okay, how do we get the constant a and b? Is basically by using the boundary conditions that we have formed in step number 2. So this is the intention of doing step number 2 here, to know the boundary conditions for the ODE so that we can apply here. Okay, so the boundary condition that we have, the first one says that x of 0 equal to 0. So if we apply to the equation that we have, okay, above, then we have 0 equals a. Okay, so straight away, okay, then we update our solution, x equals bx only. So we still have b that need to be determined. So we use the second boundary condition that we have formed, which is x1 equal to 0, simply means when small x is 1, which is b, the capital X is 0. So b is also 0. So when b is 0, then what happened to our equation? So therefore, the equation here is 0, because A is 0 here, B is also 0. Okay, so we have that. So if x equal to 0, then see the consequences to the equation star here. Therefore, by the equation star, we have then u x t equal to 0, because regardless the equation for the t, okay, our x is 0, which implies the whole thing is 0. So u x t equal to 0, so this is out of our interest, no interest. So this is not the solution that we want, okay? Because u at 0 simply means, okay, if we refer back to our graph, okay, regardless the x that we have here, okay, x3, x4, and so on, the temperature value is always 0, which is, okay, doesn't make sense. Okay, when we are talking about the heat, when we put the heat in the middle, so we can expect, okay, the neighborhood points, okay, should somehow has some temperature value. They are not 0. Okay, so it means that for the first case here is out of interest, no interest. So meaning that we are going to discard lambda equal to 0. Okay, so now see what happened to the u if lambda is positive. Okay, so lambda greater than 0, so we are going to assume lambda equals p square. Okay, so because if lambda equals p square, we can guarantee lambda is always positive. Okay, because whatever value of p, okay, you are going to square that value, so you have the positive lambda. Okay, so again by equation 1, from 1, okay, so now this lambda here is p square. Okay, lambda p square. So from equation 1, we are going to have x double prime minus p square x equal to 0. Okay, again, this is homogeneous equation. Okay, homogeneous equation. To solve that equation, we do m square minus p square equal to 0. So we have m square equals p square. Our intention is to have m, so m1 and m2. Okay, so m1 is p and the second one is negative p. So we have two roots which are distinct. Okay, they are not equal to each other. So the homogeneous, okay, if we can recall, then it should be in the form of a exponent m1 x plus b exponent m2, which is negative px. All right, so that's our equation for the x. Okay, we have constants a and b that need to be determined. Again, we apply, okay, the boundary conditions that we have formed in the second step. So first boundary condition that we have is x0 equal to 0. Okay, so see, when x is 0, when small x is 0, the capital X is 0. Okay, so from the equation of x that we have here, okay, so meaning that at the left hand side we have 0, and then when small x is 0, the exponent term is going to be 1. So we have a plus b. Okay, which means that b equals negative a, or we can have a equals negative b. Okay, doesn't matter which one. So with that, b equals negative a, then we update our solution. X then is going to be a exponent px, okay, plus b. B now is negative a, so I'm going to write minus a exponent negative px, okay, which can be written as, I can factor out the a, so that I have exponent px minus exponent negative px. Okay, that is equation for the x. Okay, we still have a, okay, in the equation. So we apply the second condition, okay, from step number 2. So we have x1 equal to 0. Okay, so look at our updated solution. So the capital X is 0 at the left and small x is 1. So we have A, okay, in the bracket we have exponent P times 1. So we have exponent of P minus exponent negative P. All right. So we now need to think, okay, at the right hand side here, which one should be 0? The P or A that need to be 0 in order to have the whole thing here equal to 0 at the left hand side. Okay, so in this equation, we can say that P cannot be 0. Why? P cannot be 0 because, okay, see what happened if P equal to 0. If P equal to 0, okay, if P equal to 0, of course we have 1 here, minus 1, which is 0, so the whole thing becomes 0, which is valid. But then we need to look back. If P equal to 0, then what happened here, if P equal to 0, lambda is 0, which is the case that we have earlier. Okay, our intention here is to have lambda is positive. So P cannot be 0, otherwise it's going to be case 1. Okay, so in this case, P cannot be 0. So since P cannot be 0, all right, and then exponent of P minus exponent of negative P also cannot be 0. Why? This is because exponent of P minus exponent of negative P will be 0 only when P is 0. Okay, when P is 0, of course, we have 1 here minus 1 here is 0. If P is not 0, you'll never get exponent of P minus exponent negative P equal to 0. You can try plotting the graph of exponent of x minus exponent negative x. You never reach 0. The only point that will make this equation is going to be 0 is when P equal to 0. But okay, here we state that P cannot be 0 because of the justification here. So since P cannot be 0, so this term here also will never be 0. Okay, so now the only thing that need to be 0 is A then. Therefore, A need to be 0. Otherwise, this equation is not going to be 0. Okay, so A cannot be 0. So when A is 0, so you can see B, which is negative A, also is going to be 0. So the consequences is then, therefore, our x, the whole thing again becomes 0 because of this one here. So A is 0, so the whole thing here becomes 0, which implies our x is 0. Again, the same justification as case number 1 from this equation, our uxt again is going to be 0 because x times t. Since x is 0, the whole thing becomes 0. Again, this is out of interest. So case number 2 also didn't work. Case number 1 we discard. Okay. Case number 2 also out of interest. So we can expect the only case that should be working is case number 3. Otherwise, we don't have the solution for the heat equation. Okay, so let's see case number 3 where lambda is a negative number. Lambda is less than 0. So we are going to assume lambda equals negative p squared so that we always get lambda is negative. Okay, so whatever value of p, you are going to square that. So it's going to be positive, and then you will multiply with the negative one somewhere here. So you always get lambda is a negative value. Okay, so we assume lambda is negative p squared. See what is the effect to the equation 1 and 2. Okay, when lambda equals negative p squared, so see the effect to the equation 1. Okay, so we have from 1 Okay, so we have x double prime. So now we are going to have plus, okay, because lambda is negative. So we have plus p square x equal to 0. So again, this is homogeneous equation, which can be solved by finding the characteristic equation first. M square plus p square equal to 0. So m square equals negative p square. So we have the square root of complex, okay, complex form. So here m can be written as 0 plus minus pi. So we have complex roots here. So then the homogeneous solution is going to be a cos px plus b sine px. Okay, we should know that exponent term is 1, okay, because alpha is 0. So we have x over there. And then we need to get the a and b by applying the boundary conditions that we have formed earlier, which is x0 equal to 0, first one. All right. So it means that when small x is 0, the capital X is 0. So we have 0 at the left. So at the right hand side, we have a cos 0, which is 1. So we have a plus b sine 0, which is 0. So we have 0 equals a. Okay, a equal to 0. Then we update our solution for the x. So we have b sine px only. Okay, so we have b that need to be determined. So we have the second boundary condition, x1 equal to 0. So it means that when small x is 1, the capital X is 0. So we have 0 at the left. So at the right hand side, we have b sine p because x is 1. Okay, so again, since p cannot be 0, the same justification as before, because if p equal to 0, so we have case lambda equal to 0, which is back to case number 1, which is out of interest. Okay, so p cannot be 0. Okay, and then b also cannot be 0. Because if b equal to 0, then the whole thing becomes 0. A is already 0. If b is going to be 0, then our x is 0. When x is 0, the equation here is going to be 0. Again, we have out of interest case. Okay, so b cannot be 0. Okay, so that we have a good solution. So b cannot be 0. So therefore, the only thing that has to be 0 is sine p, because it is not the general sine x. It's just sine p, only at p. Okay, the sine value is 0. So it's okay to have that. So sine p equal to 0. Okay, so we need to think of what is the p so that the sine value is 0. Okay, so p is actually n pi, because we know sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, so on and so forth. Okay, which can be simplified as n pi, where n equals 1, 2, 3, and so on. Okay, so p equals n pi. So if we look back at our equation here, meaning that when n equals 1, for example, then we have the equation x equals b sine pi x. When n equals 2, we have another solution, x equals b sine 2 pi x. Okay, so meaning that we have lots of solution for the x here. Okay, depending on the n here. So we can simplify by writing, so first of all, we have updated solution here, x equals b sine and pi x. Okay, but then there are lots of value of n. Okay, then we can write as x subscript n of x equals b also is bn, okay, sine n pi x. Okay, so this is the solution for the x. Okay, n equals 1, 2, 3, and so on. All right, so now, meaning that, okay, we have the solution for 1 now, which is given here. So we need to proceed with finding the solution for the 2, okay, because our intention is here, okay, to get the solution of u here. So we can proceed to equation 2. So in the previous two cases, we do not solve for equation 2 because the first one is out of interest. So we don't need to proceed with solving equation 2. But for this one, since we have the solution for the x, so we need to continue for equation number 2. Again, when lambda equals negative p squared, so see equation 2 becomes t prime plus 4 p squared t equal to 0. Again, this is, here we can consider this one as homogeneous equation, which only involved with the first derivative. So it means that the characteristic equation is m plus 4 p squared equal to 0. So we only have m only, one root only. So when we have one root, we need to consider that one as the case of distinct, okay, distinct root, meaning that the solution, okay, which is t of t equals, so we are going to have c now, okay, constant c, exponent negative 4p squared t. Okay, so careful on the variable because in chapter 2 we are normally dealing with the y, okay, but now the variable is t. Okay, so that one. Okay, so since p is n pi, okay, so therefore we have t of t equals, so we can write tn, okay, because the okay, n can be from 1 to infinity. So we can write Tn equals C, also Cn, exponent negative 4. P is n pi, so we have n squared, pi squared. Don't forget the small t. Okay, n equals 1, 2, 3, so on and so forth. All right. So with that solution of t, so now we can put in equation star. Therefore, from equation star, which is u xt, okay, that is x times t. So now we have x is what? Bn. Bn sine n pi x multiply with the Cn exponent negative 4 n square pi square t. So Bn times Cn is another constant that we can write as small bn. Sine n pi x exponent negative 4 n square pi square t, where the Bn equals capital B n times the Cn. Okay, so that's our initial solution for the u. Okay, so but we can see we still have constant Bn here that need to be determined. Okay, so in the next step, we are going to get the Bn. All right. So step number 4, sum all cases, okay, because uxt in general is the summation of u in the case 1 plus u in the case 2 plus u in the case 3, okay, but the first two cases is out of context, out of interest, okay, so summation of all cases of lambda here in standard terminology, so this is called the superposition principle. Okay, you can Google around, or if you have the textbook, you can refer to that. Okay, superposition principle says that if if u from case 1 is the solution to the PDE, okay, and u from the case 2 is also the solution to the PDE, then the summation of u case 1 plus u case 2 is also the solution to the PDE. Okay, and if we have one more, u case 3 is the solution to the PDE, then the whole thing here, the summation of all cases is the solution. Okay, the total solution to our PDE. Okay. So since the first two cases are out of context, then we only have case number 3. So this is the summation of n equals 1 up to infinity. So just now we have Bn exponent negative 4n square pi square t sine n pi x. Okay, so this is our initial solution. So it means that in some other cases, okay, in some other PDE, if case number 2 is working, is in the right context, okay, which is not out of interest, then we will need to add up the two cases. If all of the cases is valid, okay, all of the cases are valid, then we need to add all of them. Okay, but for the heat equation here, the first two cases are out of interest, so we only consider case number 3. Okay, so we have this one as initial solution. Still need to determine the Bn here. So we are going to have the last step here, which is step number 5, okay, to get the Bn. Now, step 5, apply the initial condition given in the problem to get the constant or the coefficient here. The Bn here need to be determined. Okay, so the only condition that has not been used yet is the initial condition given by the problem. Okay, so from the problem, we have u x0 equals x over 4. So this is given by the problem. All right. So if we apply to the equation that we have here, okay, so it means that when t is 0, okay, regardless the x, the u is x over 4. Okay, so from step 4, we have at the left hand side is x over 4 equals, at the right hand side we have the summation n equals 1 up to positive infinity, and t is 0. So when t is 0 here, the whole thing here becomes exponent of 0, which is 1. So what's left at the right hand side is Bn sine n pi x. Alright, so we have that. Okay, so the intention now is to know what is the Bn. How do we solve the Bn? How do we get the Bn? Okay, so this is where chapter 4 comes in. Okay, so if we can recall from the Fourier series, specifically for the odd function. Okay, for the odd function, we have the formula fx equal the summation of n from 1 to positive infinity bn sine n pi x over L. So this is the formula for the odd function in the Fourier series. So if we can map to the equation that we have here, they are basically in the same form. If we are mapping the left hand side and the right hand side, they are equal. I mean, in the same form. Okay, identical. So it means that we can say that, therefore, by mapping these two, okay, we know that fx is mapped to x over 4. And then Bn in the Fourier series is also the Bn in our solution. So that's why at the first place in step number 3, I put the Bn so that you can see easier, okay, because that is the same notation that we have used in the Fourier series. And then L in the Fourier series, okay, is 1 according to our equation, because here we have n pi x over L. Okay, so L is 1 here. Okay, so meaning that, okay, if we know how to get the Bn in the Fourier series, meaning that we can get our Bn from the given equation here. Okay, so in the Fourier series, how do you get the Bn? So Bn in the Fourier series is 2 over L, integral from 0 to L, fx sine n pi x over L dx. Okay, so all of the elements that we want is given. So L is 1, so we have 2. Integral from 0 to 1, okay, 0 to L means 0 to 1. Our fx is x over 4. And then sine n pi x over L is basically sine n pi x over 1. So we are left with that. Okay, so 4 and 2 can be simplified. So basically we have 1 over 2 somewhere here. Okay, so we can put aside. So we comes down to the integral of x sine n pi x. Okay, which can be solved by tabular or by parts. So we have positive x sine n pi x. Change the notation, be negative. So this is derivative of x is 1. Integrate sine is negative cos n pi x over n pi. And then we have here positive, and this is 0, and this is negative sine n pi x over n square pi square. Okay, so put the solution. So we have 1 over 2, and then we have the solution negative x cos n pi x over n pi plus, okay, sine n pi x over n square pi square. So we evaluate this solution from 0 to 1. Okay, so when x is 1, we have here 1. Cos n pi x is going to be cos n pi. Then we know that cos n pi is always or can be written as negative 1 power of n. So we have 1 over 2, and this one is negative cos n pi over n pi. And for the sign here, when x is 1, we have sine n pi, which is always 0. Okay, and then minus with the, when x is 0, so the first term is going to be 0, sine is also 0. Okay, so what's left now is 1 over 2, okay, negative 1 power of n, okay, cos n pi over n pi, okay, which can be written as 1 over 2 negative 1 power of n plus 1. Okay, because of this guy here. Negative here means negative 1, and multiply with the negative 1 power of n, so the index becomes n plus 1. Okay, so I forgot the n pi here, so it should be n pi. 1 over 2 n pi, okay, times negative 1 n plus 1. So that is our Bn. So when we have our Bn, so we can go back to this one here, because this is our intention to know the Bn. Okay, so you are not going to put here, okay, because this is not your final answer. Your final answer should be u, uxt. So therefore, final answer uxt equals the summation n equals 1 up to infinity the Bn. So we have -1 and +1 over 2n pi. Okay, so if we go back to this one, so we have exponent term here. So exponent -4n square pi square t times sine n pi x. So this is our final answer. Okay, so the distribution, the heat distribution follows this equation that we have here. So it means that if you want to know at the location, at certain location x at certain time t, so we are going to, okay, get the value at the right hand side here. Okay, but somehow that is not our concern. Okay, our task in the syllabus, we just want to know how to get the uxt. Okay, so later on in other application, if you are dealing with this, if you want to know what is the temperature value at certain x at certain t, you can basically just plot by using the computer program. Can be easily done, okay, by the program. So that is the solution to the heat equation, the first type of heat equation, okay, with the 0 endpoints. So if you notice, the whole solution here require more or less 1 hour of explanation. Okay, so that's very long. So in the exam, you need to answer this question maximum 30 minutes. 30 minutes. Can you do that? Of course, you can do that. Plus, you can refer to your book. Okay? You can refer to the solution that we have discussed here. Okay? So I hope you can go through again from step 1 until step number 5. Okay? If you have any questions, you can drop, okay, in the comment sections in the Google Classroom. I'll get back to you, okay, with the answer, inshallah. Okay, so we have one more example on the heat equation, which is the second type of boundary condition, which is insulated endpoint. That one is going to be in the next lecture. All right, so that's all for now.